To address this conundrum, an all-female team of researchers examined different theoretical models and tested them against optical data from the SDSS and X-ray data from Chandra. Their findings indicate that black hole feeding during this era may turn on abruptly and last for short periods of time, which means this growth may be difficult to spot. The timing of such growth may be key. The author's model suggests that 13 billion years ago, about 1/3 of supermassive black holes may have been accreting enough matter to be detectable. Just 200 million years earlier, a veritable blip in cosmic time, the number of potentially detectable black holes is only about 3%. In order to test this idea further, the researchers suggest that surveys with Chandra and future X-ray telescopes that look at larger areas of the sky in X-rays are necessary.
The Milky Way is a diffuse glow that marks the central plane of our home galaxy. It's brightest whenever the constellations Sagittarius and Scorpius are in view. Between them, we're looking toward the very center of the Milky Way. Thick dust clouds block our view of the central region in visible light, but satellites like NASA's SWIFT, which detect X-rays, can see straight through them. On September 16, 2012, NASA's SWIFT noticed a new and rapidly brightening X-ray source a few degrees from the galactic center. Astronomers quickly realized that this was a bright X-ray nova, something so rare that it's the first one SWIFT has seen. The object, now identified as SWIFT J1745-26 after its sky position, reached peak brightness in high-energy X-rays in just over 2 days. At lower energies, such as those seen by SWIFT's X-ray telescope, it continued to brighten into October. Additional X-ray behavior told astronomers that the object at the center of this activity was a previously unknown black hole. The black hole is part of a binary system with a normal star like the Sun. A stream of gas from the normal star flows into an accretion disk around the black hole. Usually in systems like these, the disk's gas spirals in toward the black hole, heats up greatly, and produces a steady X-ray glow. But with X-ray novae, there's a glitch in the disk. Gas builds up in the outer regions like water behind a dam. Once enough gas accumulates, which can take several decades, the dam breaks and a flood of gas surges towards the black hole, creating the X-ray nova outburst, and perhaps short-lived jets that blast particles outward at high energy. Instabilities in gas disks regulate outbursts in a wide range of objects, highlighting the importance of understanding why some disks are more stable than others.
Astronomers have found evidence for 5 dual supermassive black holes in the centers of galaxies, each containing millions of times the mass of the Sun. These black hole couples formed when 2 galaxies collided and merged with each other, forcing their supermassive black holes close together. Before this study, fewer than 10 confirmed pairs of growing black holes were known from X-ray studies, based mostly on chance detections. To carry out a systematic search, a team of researchers had to carefully sift through data from telescopes that detect different wavelengths of light. After first identifying promising candidates in optical and infrared data, the researchers then used data from NASA's Chandra X-ray Observatory to confirm the presence of 5 merging supermassive black holes in different galaxies. This work shows the effectiveness of X-ray data to help find such black hole pairs. This discovery could help scientists better understand how giant black holes grow and how they may produce the strongest gravitational wave signals in the universe.
For the first time ever, scientists using NASA's Fermi Gamma Ray Space Telescope have found the source of a high-energy neutrino from outside our galaxy. The neutrino came from the eruption of a supermassive black hole at the center of a type of galaxy called a blazar. The eruption jetted out particles moving near the speed of light. Collisions inside the jet produced gamma rays, the highest energy form of light, and neutrinos, ghostly particles that rarely interact with matter. 3.7 billion years later, they reached Earth. On September 22, 2017, a single high-energy neutrino struck an atom in a water molecule in the Antarctic ice. The crash produced a particle called a muon. It raced through the ice so fast it emitted a faint blue glow. When the muon reached the South Pole, it was tracked by the IceCube Neutrino Observatory. IceCube scientists found the original neutrino likely came from beyond our solar system. They alerted astronomers to be on the lookout for cosmic outbursts possibly associated with it. NASA's Fermi Gamma Ray Space Telescope found the source, a blazar it had been watching for some time. When the neutrino arrived, Fermi saw the blazar was brighter than it had been over the previous decade. It's the first time a neutrino could be traced back to a black hole, or to any source beyond our immediate galactic neighborhood. And it's an important step forward for a growing field scientists call multi-messenger astronomy, which combines light with new signals like gravitational waves and neutrinos to provide new insights on the most extreme cosmic phenomena.
What is a black hole? Space is a pretty dark place. Even so, some areas are darker than others. Nothing is darker than a black hole. A black hole is an area of such immense gravity that nothing, not even light, can escape from it. Black holes form at the end of some stars' lives. The energy that held the star together disappears and it collapses in on itself, producing a magnificent explosion. Here's where things get crazy. All of that material left over from the explosion, many times the mass of our sun, falls into an infinitely small point. Black holes can form in many ways though, and large black holes can have tens to millions of times the mass of our sun trapped in a point smaller than the tip of a pin. Some black holes trap more and more material as their mass increases. The point where all that mass is trapped is called a singularity. It may be infinitely small, but its influence is enormous. Imagine a circle with a singularity in the middle. The gravity on the inside of the circle is so strong that nothing can escape. It sucks in everything, even light. That's why it's black. This circle is known as the event horizon. An event horizon is probably what you are thinking of when you think of a black hole. What would happen, you might wonder, if we took a spacecraft near a black hole's event horizon? The answer? Spaghettification. That's the technical term at least. As our spacecraft approaches, the gravity will be so much stronger on the side closer to the black hole than at the other side that it will get completely stretched out like a piece of spaghetti. Try as you may, you would be hard-pressed to find anything weirder or cooler than a black hole. Presented by NASA's Space Place.
In 2011, NASA's SWIFT satellite caught an X-ray outburst from a small galaxy 3.8 billion light-years away. Within a couple of days, researchers realized they were witnessing the aftermath of a tidal disruption event, a star ripped apart by the monster black hole at the galaxy's center. Some of the stellar material fell toward the black hole, forming an accretion disk and a jet pointed in our direction.
Tidal disruption events offer us this rare view at the most common kind of supermassive black hole in the universe, these so-called dormant supermassive black holes. 90% of black holes in the universe don't have a lot of hot material orbiting around them. They don't form these accretion disks, and so we can't observe them. Tidal disruption events, where the stellar debris causes the formation of a temporary accretion disk, offers us a way to probe this population of supermassive black holes.
SWIFT monitored the outburst's progress and was joined by the European Space Agency's XMM Newton Observatory and the Japanese Suzaku satellite. Recently, astronomers introduced a new analysis technique that for the first time allows them to peer deep into the gravitational well of a normally quiescent black hole. Called X-ray reverberation mapping, the method charts the region close to the black hole using light echoes from X-ray flashes, similar to the way sonar uses sound to map the ocean floor.
X-ray reverberation mapping has been very successful at probing the accretion flow in well-established accretion disk structures, but had never been used to look at tidal disruption events. My collaborator at the University of Maryland and I were having lunch one day, and she says, "Has anyone ever looked at tidal disruption events with X-ray reverberation mapping?" That night, I stayed late at the office and just tried it out on this data from Swift J1644, and much to my surprise, the result was amazing, and I could see that we were looking at the structure of the inner accretion flow around a normally dormant black hole for the first time. It's not like a normal accretion flow in an active galaxy that's a flat disk. This is something that is extremely puffy, very turbulent, and we are measuring flashes of X-ray emission deep within this newly formed accretion disk.
Stellar material streamed into the developing disk, churning it into a thick, chaotic whirlpool of X-ray emitting gas, funneling toward the central black hole. Deep inside this cavity, multiple X-ray flares erupted, providing a flash that echoed throughout the region.
Previously, astronomers had thought that the X-ray emission is coming from far out in a jet. But what we're finding with these observations is that the X-ray emission is coming from flares very close to the supermassive black hole. And we can use these observations to probe properties of the black hole itself. For instance, we found that the mass of the black hole is something on the order of 1,000,000 times the mass of the Sun.
The first observations of X-ray reverberations from deep inside an accretion disk are providing new insights into a rarely observed class of black holes. They're also laying the groundwork for a better understanding of tidal disruption events and the black holes they illuminate.
Like a lot of kids, I grew up reading about neutrinos and people speculating about doing neutrino astronomy. And here I am, doing neutrino astronomy. I feel like I need to pinch myself. My name is Rupesh Ojha, and I'm an astronomer working at the Goddard Space Flight Center. I work with the Fermi Gamma Ray Space Telescope. What we have been able to establish for the first time is an individual blazar as a potential birthplace of an individual neutrino. The Fermi Gamma Ray Space Telescope has an instrument called the Large Area Telescope, which we use to monitor the gamma ray sky, the highest energy electromagnetic band. And we just noticed that there was a tremendous increase in the amount of gamma ray light coming from this one extragalactic blazar. A blazar is an extremely powerful, variable galaxy that is powered by a supermassive black hole. It went up not by a little bit, not by a few percent. It went up like 15 to 30 times its average flux. So we knew something was afoot. Later on, it turned out to be coincident, both in time and in space, with the neutrino that was detected by IceCube. IceCube is a neutrino telescope located at the South Pole, or to be more precise, under it. It consists of over 5,000 detectors that are spread out into a cube about 1 kilometer on each side. It's the world's biggest and its coolest telescope. So a neutrino is an incredibly small particle. It moves almost at the speed of light. It is nearly massless. It's incredibly plentiful, but it's very, very hard to detect because it will not interact with just about anything. If you could detect them though, because they have traveled through the universe essentially undeflected, they have information that you could not access in any other way. IceCube has detected a handful of extremely energetic neutrinos. One of them, which is called Big Bird, has an energy of about 2 peta-electron volts. To give you an idea of how much energy that is, it is about 1 million times the energy of a dental X-ray. IceCube sees too large a patch of sky to let us determine exactly which blazar Big Bird came from. The enormous increase in gamma-ray flux seen by LAT and radio flux by other Toonami telescopes let us finger the exact blazar which is responsible for Big Bird. We have long suspected that blazars are the birthplaces of such neutrinos. What we have been able to establish for the first time is an individual blazar as a potential birthplace of an individual neutrino. This is the first time that we can point and say that blazar is where this neutrino came from. Blazars are the brightest, steadily shining objects in the universe. However, many of the most basic questions about them, such as what is producing this tremendous amount of energy, remain open and unanswered. The same process that produces this neutrino could also produce gamma rays, and that would move us closer to an understanding of emission from near black holes in blazars.
Every day or two, on average, satellites detect a massive explosion somewhere in the sky. These are gamma-ray bursts, the brightest blasts in the universe. They're thought to be caused by jets of matter moving near the speed of light associated with the births of black holes. Gamma-ray bursts that last longer than 2 seconds are the most common and are thought to result from the death of a massive star. Shorter bursts prove much more elusive. In fact, even some of their basic properties were unknown until NASA's SWIFT satellite began work in 2004. Astronomers suspected that crashing neutron stars could explain short bursts. A neutron star is what remains when a star several times the mass of the Sun collapses and explodes. With more than the Sun's mass packed into a sphere less than 18 miles across, these objects are incredibly dense. Just a sugar cube-sized piece of neutron star can weigh as much as all the water in the Great Lakes. When 2 orbiting neutron stars collide, they merge and form a black hole, releasing enormous amounts of energy in the process. Armed with state-of-the-art supercomputer models, scientists have shown that colliding neutron stars can produce the energetic jet required for a gamma-ray burst. Earlier simulations demonstrated that mergers could make black holes. Others had shown that the high-speed particle jets needed to make a gamma-ray burst would continue if placed in the swirling wreckage of a recent merger. Now, the simulations reveal the middle step of the process, how the merging star's magnetic field organizes itself into outwardly directed components capable of forming a jet. The Damiana supercomputer at Germany's Max Planck Institute for Gravitational Physics needed 6 weeks to reveal the details of a process that unfolds in just 35 thousandths of a second. The new simulation shows 2 neutron stars merging to form a black hole surrounded by superhot plasma. On the left is a map of the density of the stars as they scramble their matter into a dense hot cloud of swirling debris. On the right is a map of the magnetic fields, with blue representing magnetic strength 1 billion times greater than the Sun's. The simulation shows the same disorderly behavior of the matter and magnetic fields. Both structures gradually become more organized, but what's important here is the white magnetic field. Amidst this incredible turmoil, the white field has taken on the character of a jet, although no matter is flowing through it when the simulation ends. Showing that chaotic magnetic fields suddenly become organized as jets provides scientists with the missing link. It confirms that merging neutron stars can indeed produce short gamma-ray bursts. At this moment, somewhere across the cosmos, it's about to happen again.
Parkes 1441 plus 25 is a distant galaxy powered by a supermassive black hole. It's so far away, its light takes more than half the current age of the universe to reach us. This is NASA's Fermi Gamma Ray Space Telescope, our sharpest satellite eyes on the gamma ray sky. But Fermi's effective collecting area is about the size of 2 office desks. It can't catch everything. Ground-based gamma ray observatories sport much larger light collectors than Fermi, but like traditional telescopes, they only work at night. Both MAGIC and Veritas work by catching faint flashes of visible light produced when a high-energy gamma ray strikes the upper atmosphere. This creates a shower of fast-moving charged particles that emit a glow called Cherenkov radiation. On April 16, 2015, Parkes 1441 was exhibiting high activity across all wavelengths. Scientists looking at Fermi data reported a strong gamma-ray outburst. Based on this alert, scientists on the MAGIC team began monitoring the galaxy and detected very high-energy gamma rays. That was the cue for Veritas to take a look, and it also captured the quasar's very high-energy emission. These detections were remarkable because high-energy light usually can't travel extreme distances. These gamma rays had been traveling for half the age of the cosmos, passing through all the light emitted by stars, supernovae, and everything else that flashed and glowed across more than 7 billion years of cosmic history. Astronomers call this remnant glow the extragalactic background light. When a gamma ray strikes this lower energy light, it converts into a pair of particles, an electron and a positron. The farther gamma rays travel, the more likely it is they'll undergo this process, which effectively erases the gamma rays from the universe before we have the opportunity to detect them. Parkes 1441 is one of the most distant sources of gamma rays with energies above 100 GeV, tens of billions of times the energy in visible light. That the light reached us at all provides information about the extragalactic background light when the universe was half its present age. Those gamma rays originated from the particle jet produced by the galaxy's supermassive black hole. Astronomers think they started their journey only about 5 light-years from the black hole. Escaping the galaxy's crowded central regions means this high-energy light never interacted with matter or starlight, collisions that would have doomed them to convert into particles. This is one reason why extremely energetic gamma rays are few and far between, and why astronomers prize the relatively few photons they can find. The story of gamma rays from Parkes 1441 isn't a mere tale of survival. These photons executed a jailbreak of cosmic proportions, and it took Fermi, MAGIC, and Veritas to round them up.